Well, here's a short presentation about the research I was able to do in the last months. It is about the weak approximation of the Heston model, more precisely it's an analysis of the weak convergence rates of two semi-exact discretization schemes. It is a joint work with Annalena Mickel, who recently started her PhD with me. And in fact, she was doing all the hard calculations behind the following results. And well, since time is at the moment a very limited resource for me, and since she already had recorded the talk for a different conference, I'm now taking the liberty just to reuse her presentation.
So we start with the well-known Heston model, which was developed by Steve Heston in 1993. It models an asset price, or in this version here, a log asset price, which is denoted by xt, and its stochastic variance, which is denoted by vt. The process modeling the variance is the well-known Cox-Ingersoll-Ross process. Let me just say something about the parameters. x0 and v0 are the log asset price and the variance at time t equals 0. Kappa is the speed of mean reversion of the variance process. Theta is the long-run mean of the variance. Sigma is the parameter that determines the volatility of the variance. R is the risk-neutral drift, like a risk-free interest rate. And finally, rho represents the correlation between the two processes. W and B are two independent Brownian motions. Now, our goal is to compute the price P of an option with maturity capital T, which is equal to the expectation of f of x capital T. Here, f is the payoff function of our option, and f is measurable. So for some options, there exists a closed-form solution for P, but most of the time we have to approximate P via a Monte Carlo simulation. There are several exact or almost exact algorithms to simulate this value, including the one from Brody and Kaya, but all of them have very high computational costs. Therefore, we either have to discretize the equation for xt, or we have to discretize the full Heston model to get an approximation for P. And now we are interested in the weak convergence rate of this approximation. There are some results for the weak convergence rates, especially for the Cox-Ingersoll-Ross process, for example from Alfonsi and Bossi and Diop. There are not that many results for the full Heston model. For example, we have an article of Altmaier and Neuenkirch from 2015 or an article from Zhang from 2017. There are some crucial points in the error analysis. The first one is the regularity of the Kolmogorov PDE for the log-Heston model. It's a degenerate parabolic PDE, and we need suitable regularity estimates for our analysis. Second, the discretization of the CAR process should be positivity preserving, since we model a variance here and it would not make sense to have negative values for it. Third, many of the mentioned articles above needed strong assumptions on the Feller index to prove their results. The Feller index is denoted by nu, which is equal to 2 times kappa times theta divided by sigma squared. And it controls the closeness of the CAR process to 0. Requiring a high Feller index makes the analysis a little bit easier, but it is always our goal to state theorems for the largest possible parameter range. The starting point of our analysis now were the articles of Zhang and Fihan and Pop. I will present the main results of the article from Zhang on the next slide. Fihan and Pop provided regularity estimates for the Kolmogorov PDE of the log-Heston model. Now I'm coming back to the Heston SDEs. We can substitute the SDE for Vt into the log price process. This looks now like this. And we can discretize this whole thing with the trapezoidal rule. You can see the trapezoidal rule here and here. We can simulate this because we know that Vt follows a non-central chi-squared distribution, and therefore we can simulate Vt exactly. Also notice that V and B are independent, since V is only dependent on the Brownian motion W, and as I said before, W is independent of B. Now, Jeune found that if the payoff of the option is polynomial, then this scheme has a weak convergence order of 2. The good thing about his theorem is that he did not need any assumptions on the Feller index, but there's quite a strong structural assumption on F. Now, we discretized the SDE with the Euler scheme and with a semi-trapezoidal scheme. We called it like that because we only discretized this term here with the trapezoidal rule, and this term is just discretized with the Euler rule. In our proofs, instead of directly using the payoff f, we use a function h, which is also dependent on v, as you can see here. But we can construct the payoff f such that it is a product of this h and some damping function, which is a rather technical step and not really relevant for the presentation here. The assumptions on h and f are exactly the same, therefore you can just think of h as the payoff function of our option. We found that if first h is twice continuously differentiable with compact support, and its second derivative is Hölder continuous of order epsilon, and second, the Feller index is bigger than 3/2, then both schemes converge with weak order 1. Let me add that the compact support assumption arises from the regularity results from Feehan and Popp, which we were using here. Now, if we require stronger assumptions on h, namely that it is 4 times continuously differentiable with compact support, and the fourth derivative of h is Hölder continuous of order epsilon, then we found that both schemes converge with weak order 1, but without any assumptions needed on the Feller index. If we require a Feller index larger than 1, then we can perform such an arrow expansion as it is stated here. And here we have a couple of terms of order 2, and this expression where x hat is the time continuous version of xk and q is some suitable function. We also performed a number of simulations, and I'm going to show 2 of the results now. We simulated 20 million paths for each number of time steps from 2 to the power of 0 to 2 to the power of 8. And then we estimated the rate of convergence by the slope of a least squares fit. The options we're looking at are a European call option, a European put option, and a type of barrier option whose payoff function is an indicator. I have to mention that none of these payoff functions fulfills the assumptions on the smoothness in our theorems, but the results are nevertheless quite good. Here you can see the model parameters. You can see that the first model has a Feller index of 0.63, and the second model has a Feller index of 2.01. For the first model, we estimated the weak error order to be around 1 for the Euler method, and even a little bit higher for the call. Here, it's around 1.3, despite the low Feller index of only 0.63. For the semi-trapezoidal discretization, the weak error order is surprisingly high for the call, around 1.7, and around 1 for put and indicator. The results for Model 1 indicate that our theorems could hold for weaker assumptions. In the second model, the convergence rate of the Euler method is again around 1. The results seem a little bit weaker than for the first model, despite the higher Feller index. Again, the semi-trapezoidal discretization shows a very good convergence behavior with a rate around 1.5 for all 3 options. So the semi-trapezoidal scheme might be an order 1.5 scheme in particular cases, so a deeper look into its error expansions might be necessary. So what have we shown so far? We showed weak order 1 for 2 discretization schemes and confirmed it by simulation studies under relatively mild assumptions on the payoff function and on the Feller index. Recall that for our second theorem, we didn't even need assumptions on the Feller index. Now, what are the next steps? We would like to improve the error expansion with new regularity results for the Heston PDE and use this error expansion for extrapolation. Furthermore, we are working on the error analysis of the classical Euler discretization of the Heston model. This means that we are also discretizing the CIR process with Euler. This has its own challenges since there are many ways to preserve the positivity of this process when we discretize it like that. In practice, it is used quite frequently and it works well, but there is no weak error analysis available so far. So this was my talk about weak convergence rate of semi-exact discretization schemes of the Heston model. Thank you very much for listening.